Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 30th, 2026, about 5 days ago. It reports a surprising result where a mere 3-step diffusion model, trained on bedrooms, achieved a peak signal-to-noise ratio of nearly 33 decibels when in-painting human faces, actually beating a 1,000-step model trained specifically on face data. The paper is titled, Weak diffusion priors can still achieve strong inverse problem performance. And as we'll see later, this finding suggests that under the right conditions, the quality of your generative prior matters far less than we thought. Well, Figure 1 illustrates this counterintuitive phenomenon directly. On the left side, we have a face reconstruction task where the top row uses a standard matched prior, which works as expected. However, the bottom row is the real surprise. It uses a prior trained exclusively on bedrooms. Even though this model has never seen a human face, it successfully reconstructs the woman's features by iteration 1000. The right side mirrors this finding, demonstrating that a face model can conversely reconstruct a bedroom scene, provided the measurements are strong enough. So Figure 2 breaks down the theory behind this robustness, using a simple 2D simulation. In the left panel, we see two distinct priors, an orange cluster and a green one, that are clearly offset from the true signal marked by the black star. But look at the middle and right panels as we increase the number of data observations. By 50 observations, both distributions have tightly concentrated right on top of that star. This illustrates a classic Bayesian principle. Sufficiently informative data eventually overwhelms the prior, making your initial choice of model irrelevant. While the previous figure demonstrated the concept with a simulation, Table 1 provides empirical evidence supporting the author's identifiability assumption. This table lists the score gap for random inpainting, which essentially quantifies how mathematically distinct the correct image is from incorrect guesses. In the middle column, the mean gap is consistently substantial, ranging between 0.22 and 0.28 across datasets. The rightmost column is even more critical, showing that the minimum gap never drops below 0.09, ensuring the true signal is always separable given enough data. Alright, Table 2 now presents the main cross-domain performance results across in-painting and super resolution. The top section focuses on in-painting, where the findings are particularly striking. If you look at the Celeb A column, the standard DPS baseline using a full in-domain model scores nearly 32 decibels. But remarkably, the author's method using a completely mismatched bedroom model, seen in the row labeled bedroom, actually beats it, reaching nearly 33 decibels. This confirms that a weak out-of-domain prior can outperform a strong baseline when the measurements are sufficiently informative. Okay. Having established that weak priors work, Table 4 isolates the contributions of the specific algorithmic refinements, the atom sphere optimizer, and the holdout top K strategy. The columns labeled A through D test these components individually and in combination. Comparing column A against B, or C against D, reveals that the holdout top K mechanism consistently improves reconstruction quality. The best results appear in column D, which combines both proposed techniques to achieve the highest PSNR scores across both Gaussian denoising and in-painting tasks. Well, while the previous results were promising, Figure 3 exposes the critical failure modes where weak priors fall apart. The top row demonstrates box in-painting with a large mask, and the bottom row shows extreme 16x super resolution. If you look at the far right column, the method attempts to reconstruct a church using a mismatched prior trained on faces. In that top right panel, the model essentially hallucinates a face into the architecture because the measurement is too weak to override the wrong prior. So, Table 8 shifts gears to modern latent diffusion models, specifically testing Stable Diffusion 2.1 and the Diffusion Transformer, or DIT, on ImageNet. The top section reports results for in-painting, where the author's method using DIT achieves the highest PSNR of 28.44, proving very competitive with the strong DPS baseline. In the Gaussian deblurring section below, we see a similar pattern, with their method again leading in signal fidelity. This confirms that the technique scales effectively to complex, large-scale latent architectures. Wrapping up, two takeaways stand out. First, the domain match of a prior matters less than assumed, because informative measurements effectively wash out its bias. Second, this means practitioners can often swap expensive, custom models for cheaper, general-purpose ones without sacrificing quality. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.